Hello and welcome to IEEE Soft Robotics Podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa ElDiwiny, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks. Hello and welcome to IEEE Soft Robotics Podcast. Could you please introduce yourself?
Yeah, my name is Xiaobo Tian, and I'm a professor in the Department of Electrical and Computer Engineering at Michigan State University. I direct the Smart Microsystems Lab, and our work focuses on soft robotics, underwater robotics, smart materials, and control systems.
So much for joining us, Professor. I would like to go back when you were a child. Do you have any memory where you were interested in science and technology? If you remember any memories about that?
Yeah, I think I liked engineering from my very early stage. I liked experimenting with stuff, especially circuits. I remember once I was building a solenoid when I was a middle school student. I was doing that at home without any instructions or guidance or supervision. I basically wound some copper wires around a boat, and I believe I plugged that into the wall. And the next thing I knew was explosion and huge kind of blast at home. So it's lucky that I'm still here.
It's fascinating. In the middle school and you're doing solenoid, I think it's very advanced, I think, for middle school. Yeah, it sounds interesting. Yeah. So I would like to backwards first robot you build.
Well, it's funny that I don't think I built any robot until I got into my current position, a faculty member at Michigan State. Even that, arguably, it's not me building the robots, it's my students building the robots. Part of that was because my background was in controls. Not all my bachelor's, master's, and PhD training was on control theory and some control applications. And so of course I knew robots, I have seen robots, but I never really got a chance to build robots. So the first robot that I would say my group or, when I was involved was actually soft robot kind of flavor. It was a IPMC, which is electroactive polymer. IPMC actuated robotic tadpole. I call it tadpole because it looked like a tadpole. In fact, it was Easter eggshell housing some electronics, and then there was the IPMC tail, at the end. It didn't really do much. It wiggled the tail a little bit, but we were so exciting because that was built by essentially some undergrads and some high school and middle school students. So I consider that was our first robot.
We would like to go for this in detail later because I'm personally interested in your work about ionic electroactive polymer and by IBMC as well. But before that, what is the most inspiring living creature from your perspective? Something could be fascinating for designing inspiration for designing smart material.
Yeah, I think other than humans, I still believe humans are the most inspiring and impressive creature on the earth. I think other than human, that'll be octopus. Of course, that it has been the source of inspiration for many of us in the soft robotics community. But that's still my vote because it has a lot of unique features. For example, it has 3 hearts, and people say they have 9 brains. They have blue blood. They have amazing capability of camouflaging. And if their arms is injured, they can completely regenerate their arms. So all of that, show extreme capability of doing things, right? So their suckers, their arms. So I think that's really amazing. And as I mentioned, people are all fascinated by it, and people have built all kinds of octopus-inspired robots. And recently, I'm starting to work with some biologists and experts in other areas. We try to understand the sensory motor circuits associated with the grasping by octopus, and hopefully we can translate that knowledge into soft robotic arms that are really smart.
That's super interesting, and I would like to ask you what could be the missing piece when you looked at the octopus having a 3 heart and 9 brain each arm and can regenerate if injury happen. What could be the missing piece between what we have in nature and what we're trying to replicate in soft robotics? What do you think that the most important aspect we have to go for to solve this missing piece?
I think it's not really one piece missing. I think a lot of pieces are missing uh, because, of course, we all know that octopus has and other creatures have such amazing capabilities because they're millions of years evolution, and we're trying to emulate their capabilities with, relatively speaking, still very sort of primitive tools, right? So I think there are multifacets of factors here. We need advanced hardware, advanced materials, and advanced our biological understanding. And at the end of the day, to put things together, I mean, I don't think we can ever really emulate the true capabilities of these animals, but hopefully, significant advances can be made in the coming, say, 5 to 10 years.
Okay, that's great. But I think, again, I would like to point that you have this different expertise, especially you work in automatic control design and smart material. So how do you see this combination to working in two different expertise and emerging a new research line of how to understand the smart material and designing control? If you can tell us more about how the two different backgrounds you have helped you to develop a research line of research for your lab.
Absolutely. Maybe I can step back a little bit to tell you how these things kind of merge together from my own history. So my PhD was controls, right? I was working on specifically the modeling and control of hysteresis in smart materials. Here, smart materials basically refer to things like piezoelectric actuators, chip memory alloys, magnetostrictive materials, and so on. So they all have this hysteresis nonlinearity that have impeded their use in different applications. So that's my dissertation topic, and from that, what I have gained was appreciation of material science and material physics, as opposed to just control theory. And I also developed appreciation of mathematical modeling because I think that is a conduit from the physics to to mathematical representation, and then we can apply control tools. So to some extent, I still feel as a control engineer, I think modeling of the system is maybe more important than just the control methods, because oftentimes it suffices to use simply the existing control tools. What we don't have, especially when we deal with new materials or new robots, is the set of models, right? How do you describe that? Once I can cast that in, the familiar language of control, dynamic systems, I will have a way of hopefully controlling those. So that's, I think, the most important gain from my PhD study. So when I started my faculty job at Michigan State, I looked into different materials because my PhD was on magnetostrictive materials in particular, but people all advised me saying, now you are independent. You should not just continue only with your previous path. So we need to find something new. So that's why I looked to electroactive polymer materials, right? So So once I have, initially we just purchase some samples, and gradually we start to read the papers and exploring fabrication of those materials ourselves. And further down the road, I just told you about that robotic tadpole, and people were very interested, and they say, okay, that's really really cool. And then that got me excited, and we start to look into more seriously about robotic fish. And so that's how everything sort of evolves. And to today, we actually have pretty, I think, active program in general in robotics. So looking back and looking at your question, I really think this is this is really useful in terms of combining material physics with models, with control, and even look at the scale of robotics, of course, which is a bigger system than just a single actuator. I think it is really useful and instrumental to put like physics and those mathematical models and new tools together. Right? So that's sort of mutually beneficial and mutually, I would say, promoting.
I think you said a very interesting point, and I would like to split it again about the modeling part. You say that modeling is much more important than the control algorithm you have to come up with, whether it techniques. But may I ask you why modeling is so challenging? And which level of modeling you have to consider while you're working? Which scale of modeling? And do you have the feeling or perception modeling is underrated in soft robotics research?
I think people in software robotics have actually developed a strong appreciation about modeling, because people have realized that soft robots are very different from, say, rigid robots, right? Which are already fairly well characterized, in terms of their kinematics and dynamics. But so I don't think that this community lacks appreciation of the use and the challenges of modeling for soft robots. It is probably, the other question, basically, what is the right solution to the modeling challenge? For that, I personally, I'm struggling too, right? Meaning people have looked at different ways of doing it, but it's just so complicated. I think that the thing is not just things are soft, just because there are so many things involved. Sometimes not just material, but also different mechanisms like stiffness tuning mechanism, and and then you have other, maybe novel environmental factors, right? What are you interacting with? So it's just sometimes I think it's just too many things involved. The challenge is, what do you trim? What do you keep? And at the end of the day, you can still get something meaningful in terms of understanding the physics, as well as useful in terms of the control design. There are different ways people are trying, including some data-driven approaches. So I'm still looking with interest how the community can come up with good solutions, and then we're also trying to do our own part of the job.
Interesting. And do you think because modeling is time-consuming sometimes, are you with the idea that you have to take easy approach, or maybe applicable approach like data-driven, for example, or empirical result, and then you can come with coupling for modeling, for example, such technique in ionic conductive polymer, or just you have to go to modeling? Which technique you think could be feasible for a student listening to us? You have to invest a lot of time in understanding the modeling, or just you have to take easy techniques to describe system, and maybe missing parameters? So we speak about here what would be significant parameters in the system, because you don't know what could be the significant parameter yet. So which approach do you advise a student if they are working in soft robotics?
So I still strongly encourage, no matter what, everybody should try to understand the physics of the materials and sensors and actuators involved, just to give you better understanding what you're working with, right? I strongly discourage people from just saying, okay, I'm going to take the input-output data, let's do data-driven modeling. Because at the end of the day, you would only have something that's empirical and not physically insightful and not able to generalize to more common situations, right? So I think first of all, no matter what you take at the end, you should try to understand the physics. And then on the other side, I think we do need to consider what would be practical, right? There are a lot of things in the literature. There are different tools available, and maybe we cannot always link the data to a physics-based model, right? It depends on what's available. But we having said that, yes, we work with what we can, and there's no shame to say, oh, I'm not looking at data-driven models. No, frankly, we are also looking into data-driven models at this point, right? So I think it's a very open field, and we don't want to restrict us to any particular narrow corner when it comes to looking for solutions.
Great. So coming back to smart material, because indeed your lab has been doing great work in smart material. But I would like to ask you, do you think of the community, to which level do you think we really exploit the smart material functionality? To which level do you think we really understand how we can use a smart material in a proper way? And maybe the question related here, and we ask this question, how the controller can get the task done without destroying the natural dynamics. And of course, here we speak about smart material because sometimes we had this, it's happening. It could, you try to get certain behavior, but the material have highly nonlinear, especially for ionic conductive polymer. And that's maybe argument here. What's your thought about this statement?
Yes. Well, I'm biased. As I told you, I have my background in controls. I don't think control would destroy anything if you do it right. Yeah. So yes, I think that is the right thing to do. Meaning for us to create a control-oriented model and then design controllers accordingly to generate desired behavior for actuators or for robots. So I don't think ever you say a well-designed controller will destroy the nice, say, nonlinear dynamics of soft materials. Having said that, I also agree that control techniques maybe or new control techniques need to be looked at, especially when dealing with soft robots, because as we all know that soft robots are very adaptable. Sometimes the interaction with the environment automatically drive the robot toward the right path, right, or the right behavior. So I think it takes some thinking when we design controllers. What is the minimal complexity controller that we can develop to get the desired outcome? It's not always saying, okay, let's go to a 1,000 dimensional system and then try to do a controller based on that, right? And apply that complicated control to the system, because sometimes it is not necessary. But again, to what level we should let that happen, right? Because for example, if you have a soft robots, you said, okay, it's okay, we can have collision. So the environment interaction will force it back to, whatever, the right constraint. However, we also have to consider this is really still engineered object, right? They might still break, they might get damaged. So there is also I would say limit how much we can let the environment do the job. So everything is different. The experience of we working with different projects tells us that we really have to consider the real challenges when you have applications, and from there you can derive how much tolerance I have in terms of sort of self-adapting. Let the soft robot to do self-adapting, right, when interacting with the environment, and how much of it we have to control so that we keep the actual robot safe.
That's super interesting. I would like to ask you here, maybe a student asking, what could be the limitation? Because you said that there's a limit. So if we can ask this question, what could be the important parameters you have to consider in designing control and considering the limitation for soft robotics? What limitation you have witnessed for the controller, a traditional control technique in soft robotics?
Yeah, so maybe I can bring up one example, not necessarily for control purpose, but maybe it's quite I would say useful to kind of to see the point here. One of our projects deals with developing a soft sensor for detecting the suction of sea lampreys. So sea lampreys are native species in Atlantic Ocean, but they are invasive species in the lakes around, Michigan, like Great Lakes. So one way that we need to monitor and we need to control these species, right? So one idea we had was to have soft sensors, almost like you can think of soft panels mounted in the natural environment, for example, rocks or any other path that these animals will travel through. These animals like to suck because when they are tired, they suck to the surface to rest, okay, against the flow. And of course, sucking is their means of survival as well, because that's how they attack host fish and take out their body fluids and so on. So anyway, so we have this project, and we have developed a very nice, I would say, capacitive pressure sensor that is able to detect both positive and negative pressure. Right. So the idea is when you have the animal sucks to the panel, the rim of the mouth will be pushing against the panel, so therefore that's positive pressure. But because it's sucking, so the cavity of the mouth will generate basically the negative pressure, right? So so we published a very nice paper on that, and we were very hopeful, okay, when we start testing on animals. Now there are other challenges that we have experienced. Number one is things went very well when we test the device with a vacuum suction cup. Okay, it shows very clear pattern, of the suction, of the pressure distribution, but because animal itself, as we know, is alive, right? So there are tissues and there are a lot of things going on there, in the body. So they are very important source of capacitance. So when we try to detect the suction, and we were having huge trouble because when the animal approaches or sucks, that capacitive disturbance totally overwhelms the sensor signal from just the pressure itself, right? So that's one thing. That the other thing is, these animals have teeth kind of protruding out. So when they suck, they kind of also grind the sensor with their teeth. So in a few rounds, we found the sensor was damaged. Okay, so in that case, so this example, I think there are a few lessons we learn from here. Number one, as back to our question here, you always have limitations for especially our engineered sensors, actuators, or robots, right? And these are realistic examples. When you put your system in test, okay, have you really thought about what these guys will have to go through, right? So for this case, we didn't think the teeth will be working against us, right? And the second thing is, for realistic challenges, such as this one, right? There are many other factors that could work against us. So really, I don't necessarily view this as negative. Instead, we view this as opportunities because we really want to put a solution there. And in order to do that, we have to test, discover the challenges, and figure out new ways of doing it.
That's wonderful. And maybe also the other question we have about ionic conductive polymer, IPMC. Why there's resentment about the material? Sometimes we have a very slow response. If you have a higher force, it will be slow bandwidth. And there's always a trade-off between the mechanical performance and the response of bandwidth. Why do you think we have this trade-off? Do you think we can have ionic conductive polymer IPMC with high forces and high bandwidths? And I don't know if you agree with that. I think in the community, we still accept this limitation, and maybe there's disappointing about this material cannot really make a significant applications of robotics. And that is something we receive comment about, that how we can enhance the material that has really interesting feature, low current, and there's really a potential, but still there's a huge limitation behind it. How we think we can advance and move forward, having high forces and high bandwidths for ionic conductive polymer IPMCs?
That's an excellent question. In fact, I would generalize, your question. So now you see I'm trying to avoid answering the question. I actually would generalize your question to say, can you give me any actuator, any smart material that is able to deliver large force, high bandwidth, large displacement, and with small power required? I think this probably, my personal opinion, is the most important challenge facing our community if we really want to pursue things that we think are, very cool, like octopus kind of robots. Of course, people have sort of got around that problem by using more traditional actuators, right? Like motors or let's say pneumatic actuation, which are very effective. But really, if we want to think about very compact soft robotic systems, I would really prefer not to use, say, the pneumatic sources and all the valves and all these motors and all these wiring in order to do the cable-driven type of actuation. So that is one, I feel, the most important question to me. And unfortunately, I do not have an answer. And I think our community really should all work hard on this. I cannot name an actuator that meets all these requirements, yet they are so desirable. So if you look at biological muscles, right? So we have been talking about artificial muscles for so many years, and we're still very, very far off.
Great. Maybe ask you what could be the pain points just you think we have to work on. Do you think it's about modeling again or designing? What is the key for solving this question? Is it modeling or designing? Or
I think the ultimate breakthrough may have to come from on the material science side. We need to have new materials or significant advance on existing materials. It's not just a little bit of tweak here and there, and maybe something completely different. Because if you just look at these different actuators, they always have there are some thermally actuated actuators. They can produce force, nice force and nice displacement, but they're slow, right? So I think ultimately, modeling alone, I don't think that will get us very far. Because this is like, okay, you can do optimization if you have something existing, but really, I hope the community can come up with some novel ways of synthesizing materials. And fabrication, of course, fabrication has already been advancing really rapidly in the past few years. That has resulted in significant, I would say, advances in things like sensors. Right? You can do 3D printing of all kinds of materials that allows you to do sensing. So I'm less worried about sensing than actuation, when it comes to miniaturization and integration.
Yeah. So maybe we can go to the controller side. If we ask you what kind of nonlinearities you have to keep or remove for soft robotics, because we know that nonlinearities can bring opportunities for buckling, etc. But if I ask you what kind of nonlinearities you think when you work in your system, that something could be useful and that something could be detrimental for our soft robotics. What could be two scenarios for the bad and good side of nonlinearities for soft robotics?
Well, as you just mentioned, there are certain nonlinearities that are very beneficial. People are exploiting those for achieving fast response and sometimes less complicated control, like buckling or biostability of different structures. Their softness, right? So is certainly, I don't know how to characterize that as nonlinearity, but certainly is an important factor when we try to keep or exploit in different applications. In terms of nonlinearity, I think, of course, a lot of materials exist hysteresis, right? I mean, which actually is the topic dear to my heart. These include all the smart materials we are aware of, as well as these soft, in general, soft materials, even like new soft pneumatic actuators. And I would not find any good reason to believe those nonlinearities are any beneficial, right? So they should be taken out in most cases. Another thing could be because of the softness, maybe you will see long creep, because sometimes we have sensors that they really have really long, I would say, time constants, big constants, which makes it really challenging to have accurate sort of reading of the measured signal. So again, I guess this is not exactly about control, but it's maybe it is. So these are things that I think are not non-desirable, and we should try to find a way to mitigate.
Great. So if I ask you were there any direction you thought would work out very well, but empirical result proved something else? Would be interesting for you, and you didn't expect it when you have in the series was different.
Yeah. Maybe we should go back to the previous example about the sea lamprey sensor. I don't have a good insight as to one direction. Okay, I thought it would work, but it doesn't work at the end. But I think in reality, in many, I would say, projects that we have been involved with, we thought, okay, this is a great solution, at least on paper. But when we go to the real wild world, often turns out that's not a good solution, right? So the example I just gave you, we thought this is good pressure sensor, but we didn't expect the animal approach, right? Or animal attachment would directly cause disturbance of the measurements. And we didn't anticipate animal teeth would create the sort of destruction. So I think maybe a general lesson here is, or general advice is, to really put our research in the context of real application. And the final test or metric is, have we succeeded in terms of delivering that application by putting your device through that real life test. So back to your question, I don't think there's, at least I'm not aware of any specific direction, but I feel a lot of ideas that we had initially may not work in the real application, especially if we have not tested, okay? And involving those tests, throughout the project or throughout the research would give us new challenges and new opportunities.
Yeah, thank you. So if I ask you what are the biggest technological roadblocks that could face soft robotics in short term and long term, Do you think the community have to focus and address these challenges as soon as possible?
I would still say, which we already covered, actuators. Yeah, actuators that are compact, low power, delivering large force, delivering large deformation, and consuming small power. I think this is even now it's a challenge we're looking at, but I don't know when this challenge can be overcome. So it might be a long-term issue.
Okay, so coming back to the speaking different languages, and I think that's something we brought every time in the episode, that how we can overcome a challenge of speaking different language. And that's something we witness when you work with material science and control expert. There's something we don't understand each other, and it takes a lot of effort that we have to come in the middle page so that we can understand. How you see this interdisciplinary feature in soft robotics going now? Do you think it's going in the right direction, or still we have to make more effort, so that we can make the desired end goal for soft robotics, the field?
I think we have come a long way, especially in this community, soft robotics community, because if you just look at active researchers in this field, they have different backgrounds. So that's good news. In general, I think you have raised a really good question. Whenever, when it comes to interdisciplinary or cross-disciplinary collaboration, you face this challenge of language barrier. For example, a simple word like modeling, right, or model, could mean completely different things between two people, which I personally have experienced, right? So I think what we need to do is to have more conversations. Like in some of our research projects, they were initiated not just by, hey, a phone call, okay, can we write a proposal together? It's actually initiated through sometimes years-long conversations. We just sit together, have coffee or have tea, or just sitting in the office chatting about each other's work, asking questions. What do you mean by that? What do you mean by this? And find a common ground, and ultimately we can learn each other's language, right? Because that's really important. And then we can start to talk about how do you put, say, motor learning with soft robots, right? And how do you address, how do you capture that dynamics of learning, okay, through maybe some data-driven approaches or some dynamic system approaches, right? So it always takes years long of conversation for us to really come to agreement. Okay, this is really something that we should work on, right? Because once we are awarded the grant, we know what to do, right? So I think this is really important. And we at Michigan State, we have a soft robotics sort of gathering, people from material science, from, of course, robotics controls, and medical, right? We gather together regularly and talk about different ideas. So it is. I don't think it's unique for this field. It is really important for all such endeavors. And nowadays, especially if you look back at the context that we were just discussing, right? If you work on real world applications, you have to involve people from different areas, domain experts from different spaces, right? So in that case, you have to be able to talk to each other, and there's no way to take the shortcut.
Yeah, great. Yeah. The question again here about how can we enable more inclusive culture around competitive idea. I think that's something we face in academia, that there's a challenge and competition between different ideas for securing funding grants. And there's a competition happening. So how we can make sure this intellectual inclusiveness in ideas in the field?
I think we all have to keep an open mind. As let's say a professor myself, I welcome different ideas from my students. Right? Some students have really, really crazy ideas out of the box. Some students have less, I would say, risky ideas. But in any case, I wouldn't say no at outset. I would say, okay, tell me more, right? And then if I cannot convince the students, I say, okay, go ahead and explore and come back and let's discuss again. So I think we have to encourage different ideas. You never know what idea or where the idea would take the research, right? So it's I think it's critical to not to basically silence any sort of voice or any sort of ideas. We can always debate, but we can agree to disagree, but don't just silence people, including especially I think people from I would say disadvantaged groups, right? So that's important.
Good, but I think here maybe the argument, or maybe realistically speaking, sometimes when you have maybe ideas outside the box in academia specifically, there's assessment for the high risk and low risk, and that's associated with funding and make sure that you run in academia, and we know about that. So how we can make sure that we keep innovation or maybe ideas maybe outside the box and completely new, and also with mitigate risk, that you can secure result at the end of the day. This is the problem we have in the field sometimes. It happens.
Yes.
Yeah.
So of course, I have to put this in context, right? Or examples. Let's say I'm sitting on a National Science Foundation panel, okay, reviewing different proposals, and that comes up a lot, right? So that kind of arguments come up a lot. People say, "Oh, I really love this idea. That's out of the box, exciting, novel, and if this is successful, it'll be great." And then another person would say, "Hey, wait a minute. This idea is great, but I don't think this person has the right background, or I don't think they really considered all the different details, right? So and there is a great chance of failure." So that kind of argument really, I think it's important. That kind of debate is important. Ultimately, who wins the argument, right? So I think there is continuum in between because there are sometimes out of box ideas. There are clearly holes there, right? They're not, they will not work. But there's some other ideas. It's just a lot of uncertainty, and nobody says it's not going to work. So it's up to sometimes, of course, the panelists like us as well as the program manager to make the call. If they feel this is worth it, right? Then maybe start off with some smaller amount of funding to let them explore, and then when they come back with more evidence, more proof, then I think more aggressive effort or funding effort should be put forward. So it's not like, I of course I wouldn't go with any risky idea we should fund, right? So that there is definitely, we say, high risk, high reward, because there is risk of failure, and we do have to be able to use limited funding more in a wise way, right? So but on the other hand, if anything, that we should encourage exploration, and at a certain point maybe putting more resources.
Yeah, I agree with you. So if I ask you, as you are BI of your lab, how you ensure with your team that soft robotics you develop is beneficial to community, or maybe in a shorter term for the community surrounding you, how you bring this discussion to the table?
We do that all the time. In fact, we try to answer the question, what if? Why are we doing this, right? So we always have a background sort of application in mind. Maybe that's also, all the case every time when we submit a grant proposal, because we want to know how this is ultimately benefit society. And if you look at the app, the projects we have, we try to link all the fundamental research to the future applications. Like the lamprey, sensing is one example. We have other soft robotics related projects, right? Octopus arm or artificial arm, that of course is linked to future maybe smarter prosthetic devices, right? We are working on soft robotic gloves that hopefully can help us understand motor learning for improving rehabilitation, for example, and so on. So I think it's actually for soft robotics, it's really easy to make that connection, fortunately. And the question is how do we get there, right? So it's not like, okay, I propose this and then I drop that, once I have the support or financial support, I drop that final goal. I just work on, okay, nice papers, right? So I think that's sometimes we should try to be careful about, right? So ultimately, yes, we want to work on fundamental sciences and engineering technologies, and ultimately let's put all those developments into test and see whether we can get closer and closer to the original goals.
Thank you for the detail, and thank you. So we are close to the end. We have a few questions left. The first one: do you think ego is important for the researcher?
Depending on how you define ego.
Interesting point. If you can define ego, that would be great, because I think there's a lot of misconception about ego.
Yeah. No, that's a good one. I think being confident is really important. If ego means being confident, yes, it's critical, because that allows you to uphold your belief, especially when you are, let's say you are a student, you are trying to convince your advisor, right, on results or on ideas. I think having that confidence is really, really important. Having said that, I think the real, successful and confident researchers, they all have sort of a common trait, which is very open mind. They are not going to say, hey, I said this, but you're trying to counter argument, therefore I'm offended, right? So really, I don't think we should be offended if somebody else raises different ideas or different opinions, and that's something that I deal with almost on a daily basis with my students, right? So they know I'm not going to be offended, so they will challenge me, which I think is really, really important.
That's a great advice, yeah. So if I ask you what is the most important qualities you have gained while working in academia and something you have to maintain for your journey?
So I think, right, I think, as a researcher, if we want to stay active, and we really need to be curious, and we need to be imaginative, and also be adaptable, meaning you cannot just feel comfortable working on the same stuff over and over, or in a very incremental manner. You really want to look at what's happening around you, in the landscape of technology development, and what your expertise could be leveraged to help advance the causes, right? So we have to be adaptable, in the sense that we build our core. Each of us builds our core expertise, but that expertise should be developed, evolved, and adapt to new challenges and new applications arising in the horizon.
Mm-hmm. Yeah, that's great. And what was the best advice was given to you, whether personally or professionally, and was life changing for you?
So maybe nobody really gave me that particular advice, but I observed when I was a PhD student, one of my advisors mentioned something like he learns from students, right? And I found that really, really useful and true when I became a professor, because students are very curious, they are very energetic, and they are passionate, they have fresh ideas. So I love to learn from my students, and I think this is, everybody has limited bandwidth. Professors really have limited time, right? So they have good ideas and they have wisdom, but they don't have that much time and they don't have that much energy. So really, learning from students I think is one of the biggest. I think, I would say, I don't call that lesson, but that advice for myself, right? And for maybe every other colleague. Of course, you can generalize that to basically listen to other people, right? So we all have very limited bandwidth, and we know very little by individuals. So really, it's good to have open attitude and say, hey, teach me something.
That is a meaningful advice. I agree with you. And finally, do you have any final words to the soft robotics community you'd like to say?
Well, I think it's a great, very promising field with many, many hopes and also, unfortunately, some hypes right now. So I would encourage and challenge everybody, especially our young students and peers, identify some real applications of impact and work on those, keep at those until we see success. So don't just stop at, okay, I have a paper, right? So see whether you can finally nail it and have an impact.
Thanks so much, Professor, for this interesting discussion. I really enjoyed it. Thanks so much. Thank you.
My pleasure, and thank you for this opportunity.
So yeah, thank you. And